Welcome back to Frustrated User Guide. Today we have another episode designed for kitchen table technicians. That would be young people that would like to fix their own electronics on their own kitchen tables. And we have a collection of 8 multimeters, 6 multimeters and 2 multi-testers. These are the same group of meters that we used in a previous episode called True RMS or Total BS. Now, in that episode, we proved that so-called True RMS multimeters can be incredibly inaccurate measuring AC voltage. Even this $500 amp probe, incredibly inaccurate. So today, the device under test is going to be 1000 microfarad, 16 volt capacitor. Now, we're going to check the capacitor mode on all of these meters, and we'll see which, if any, are accurate, which, if any, we can rely on. Now, the device under test came from a DeWalt DC012 job site radio that I was working on, and it's this one. 1000 microfarad, 16 volt, and you can see it's on pin 12. Now this is a little switch. VCC comes in and switches off of pin 12. Now this power amp chip was several pins shorted to ground. So when that happens, of course, you check all the associated components, and so that's where this came from. Now, the results, which we'll try to duplicate right now, are in this spreadsheet. And this is worth studying. But let's get started. Let's get some of these meters hooked up and see what they say. See if we can verify these results that I took just the other day. Now, the first capacitor meter I ever owned is this CX7705. I first saw this at a Ken Gordon computer show up in Boston in the either late 80s or mid 90s. The vendor did an excellent job showing this meter at the show. It was Alpha Electronics in Princeton, New Jersey. I don't know if those people are still there. I do know they weren't actually selling these at the show, but you had to mail order it, so that's exactly what I did. Got home and put in my order. Now, the advertised accuracy of this meter, which I'm going to say is at least 35 years old, is 1%, and I have been using it all that time. So hundreds, perhaps thousands of caps have been tested on this meter. So we're going to start with this and test this cap. First, we're going to short it using a coin. We'll connect up the leads. 1000 microfarad, 16 volts, 85 degrees centigrade. Use the 2000 microfarad scale. We'll turn it on, see what happens. And we settle down at about 860 microfarad. What did we get last time? All right. That would be this one. Last time we got 869. So first thing we learn is that capacitor measurement changes from measurement to measurement and from day to day. It's just the way it is. So right now, this one, 860 microfarad. All right, let's go to the next meter. So this is my 1991 Fluke 12. I actually had the CX 7705 for several years before I got my Fluke 12, so I would say I had this in the mid-80s, mid to late 80s. Fluke 12, as you know, I've said many times, this is the best meter I've ever seen for electronic servicing. Capacitor test. I short out the cap. We're using the same test leads because we don't want test leads to skew the results. So these are the test leads from that first capacitor meter. Same leads. Device under test has been shorted. One of the things about this Fluke 12, unique, what you're witnessing right now is unique. It shows you if the cap is running. And you can see that this device under test does not settle down. When I see this behavior, I replace the cap. I don't know if it's really measuring 900 microfarads or some other value. I know it's running. 859 it says now. The last time I used my Fluke 12, it settled down on 915. So what would we say it was today? 900? 2 days ago it was 915, today it's 900. But it's running. And that tells me something is strange. And if we sit here long enough on this Fluke 12, you might see this cap go all the way down to 689 microfarads. That's the lowest I've seen it dip, all by itself. Something going on with this cap. The Fluke 12 is the only meter that shows me that. So, okay, today we're going to say it's, what do we say? 900. Let's try the next one. All right, next up we have a Fluke 17B Plus. This is relatively new. It's only a couple of years old. Using the same test leads again. We'll short out the cap using a coin. I turn this on, put this on microfarad. All right, what are we going to get? This is a very slow meter. Unlike the 12, which reads capacitance value almost immediately, this can take 10 to 12 seconds, and we've settled down on 926. Now remember how the Fluke 12 showed that the cap was running. This is also 26 microfarad more than that was averaging just a few minutes ago. Now what did the Fluke 12 say a few days ago? It said 915. Nope, excuse me. A few days ago the Fluke 17B said 930. So pretty consistent with what it said a couple days ago. But it's not showing the cap running. Now the accuracy on this meter is given as 5%, plus or minus 5 digits. So you can round this up to 932 or 923. Then take plus or minus 5% and add it or subtract it from that. But okay, that's what we got here. We've got 928. Move on to the next one. So now we've got a Harbor Freight Centec CM300. This is a $20 meter. Quite a step up from the red ones. Short the cap. The problem with this meter we proved last time, it's can be quite inaccurate, ridiculously inaccurate. Let's see what it does here. And we get 880 microfarad. What did we get last time? Centec CM300. Accuracy is given as 4%. And last time we had 898 microfarad. Today we've got 883. So once again, we see that every time you test a cap, the value changes. But for what it's worth, we're getting 884 on this one at the moment. All right, on to the next one. Okay, next we have a B-side ZT-QB9. This meter is also only 2 or 3 years old. It was inexpensive, about $25. Has a tremendous amount of features. And I originally really liked this meter until True RMS or Total BS revealed just how inaccurate the AC volt scale can be. So let's see how it does for capacitance. We got our same device under test. We're going to short it out using a coin. Oh, I'm going to turn this on first. All right, we don't want voltage. That's what we want. Okay, this one tells us 891.5 microfarad. What did we get last time? 897. All right, on to the next. So next we have our $500 amp probe. This is an AC DC 52 NAV. Very expensive meter, most expensive meter I own. We'll put it over here on capacitance. Short out the cap. Same test leads. A little bit of running here. 862, 864. Don't like the fact that the hold and the light are on the same button. 881. What did we get last time? 895. Okay, so it's really moving here. So what value do you settle on? Don't like this meter. Don't like it at all. But we're going to 860, 863, 865. Last time was 895. Now, what do you take? Thank you for blinking out on me again. Wonderful. So, okay, it is what it is. Let's go to the next one. Okay, next we have an MK328 component tester. Now, I've often said, and I'll say it again, if I had to give everything up and keep only 2 test instruments, what would I keep? Well, obviously my Fluke 12. Not giving that up, not selling that for $1,000. And I would want my MK328. This was only $30 brand new or so. And this has allowed me to fix very, very difficult problems to solve. Very, very difficult problems that prior to owning this meter, I had been unable to solve. So wonderful, wonderful test instrument. Don't want to be without this. So I'm going to hook up the cap. We'll see what this one says. Short it out on the coin. Doesn't really matter how you hook up these leads. So I'll hook up yellow to positive and green to negative, but it doesn't matter. We'll turn it on, see what it says. Hopefully the camera is catching that. Shows that we have a capacitor, 838 microfarads. We're losing 1.5% voltage. Equivalent series resistance is 0.14 ohms. But this is what we're looking at right now, 838.4. Wow, we have seen everything. 838 all the way up to over 900 microfarads. These are all precision test instruments, right? All right, let's go on to the next one. All right, next we have this NERSI DSO-TC2 little mini portable oscilloscope. This is relatively new. Just got this year. I really like it. Using it a lot more than I thought I would. It's so handy. Okay, you get the idea. Now, in order to fully understand what's going on, it helps to transfer our handwritten data into a spreadsheet. So here I'm using LibreOffice Calc. And on the first row, we note the device under test. It's 1,000 microfarads, 16 volt, 85 degree capacitor. On row 2, we put in our column headers. So instrument would be the first column. And in the second column, we have the cost of that instrument. This would be the manufacturer's suggested retail price. In the third column, we have the accuracy of that instrument. This is taken right from the user manuals. And in the fourth column, we have the results that we measured. Now, once you put in all of this information, very important now, the next thing to do is you select the range. So I'm clicking here on the second row and come across. Okay, now I have all of our data. Now, we go up here to the data menu and we select auto filter. Just click on it. Don't have to do anything else. Now you notice that having done that, we now have these downward pointing arrows over all the column headers. So now we can sort the results in ascending order or descending order. We can sort by the cost of the meter from most expensive meter to the cheapest meter. Sort descending, most expensive at the top. Sort ascending, cheapest at the top, most expensive at the bottom. And when you change the sort order, the rest of the data gets sorted along with it. So you're not losing your relation between these fields. We can arrange the meters alphabetically. So now we have amprobe at the bottom. That's backwards. Let's do it this way. Okay, now we got the A at the top, A, B, C. Okay, very good. So, we look at let's sort results. Let's sort it ascending. So this is our lowest value. It came from that FN little yellow oscilloscope. Accuracy is not specified, but we recorded 816 microfarad on that scope with the little component tester that's built into it. And on the Fluke 17B, we recorded a high value of 930. So the difference between 930 and 816, if you do the math here, that's 114 microfarad difference, or it's 11.4%. So how do we know that's 11.4%? Because every 10 microfarad is 1%, and every 100 microfarad is 10%. Did you know that these expensive test instruments could vary by 11.4% when measuring electrolytic capacitors? Now, the higher the value of the capacitor, the more inaccurate the measurement. The lower the value of the capacitor, the more accurate the measurement. But 1,000 microfarad is a very common value. And we're seeing 11.4% difference. Who would have guessed that that little FN scope would give us the lowest reading at 816 microfarad? And here's our Fluke 17B Plus. That's a current model. That gave us the highest reading of 930 microfarad. But wait, it gets worse than that, because the accuracy of this $167 Fluke, it's plus minus 5%. So 10% would be 93. So half of 93 is like 46.5 microfarad. So this could be a high of, according to this, if you're using the Fluke, you have to figure this could be something like 976 microfarads, or it could be like 884 microfarads. That's just a huge difference. Now, if you've only got 1 meter and you're relying on the result that you get with that meter, how much confidence can you have in that measurement? Well, let's go with the most expensive meter. That would be this Amprobe at $500. We're going to round this off to 2% accuracy. So 1% is 10 microfarads, so 2%. This could be anywhere between 915 and 875, according to the specifications of the $500 Fluke. So what I take away from this, here, let's arrange by cost. Our cheapest meter, this would be the Harbor Freight Centec CM300, 4% accuracy. So it could be 40 microfarads higher or 40 microfarads lower. According to that very cheap meter, this could be 938 microfarads. Could also be 858 microfarads. How do you have any confidence here in anything? And I can tell you from experience, if it's within 20% of its stated value, it's not what's causing your problem. And you can take apart brand new equipment that's working perfectly or old equipment that's working perfectly, and you're going to find huge variations, plus or minus 20, and that thing is still working perfectly. So just because I pull out a cap and I'm seeing these low values, I know in my experience changing that cap is not going to fix the problem. It just doesn't. So I'm not here to argue with anyone. Lots of people love to change all the electrolytic caps in whatever device they're working on. I'm not arguing. I'm just saying that if you're dealing with a problem, changing the caps does not always solve it. So let's look at what does solve the problem. Okay, how to tell if an electrolytic cap is bad. Number 1, is it leaking electrolyte? Is there any fluid leaking out from the bottom of the cap? And sometimes you can't see that. A lot of times, here's number 2, you'll get this smell of rotten fish, but a lot of people don't know what rotten fish smells like. Believe me, it's a very terrible smell. But sometimes the cap will just be starting to leak, and there'll be no puddle on the board. And you have to actually desolder the cap and look underneath it to see if it's wet. And sometimes you can't see it with the naked eye. You can't smell anything. You have to shine a UV flashlight on it, an ultraviolet flashlight. These are pretty cheap. Without the UV flashlight, you might not see that it's leaking. And in my experience, if a cap is leaking, you must change it. And you must also change all the other similar value caps. On that printed circuit board, all the ones that are manufactured by the same company and are of the same value. Because if one is leaking, all the rest of those similar value caps made by the same company are also going to leak. Then the third thing, we used to see this a lot maybe 10 years ago in Samsung televisions. These were the bulged, swollen caps. Obviously, if you're seeing it exploded out the top or bulged in any way, you must replace it. Number 4. ESR, equivalent series resistance. If you have an ESR meter and the cap is very much out of range, that's part of your problem, or maybe your whole problem. Now, I remember years ago, the 1 microfarad 100 volt, 1 microfarad 160 volt caps that used to be in the CRT socket boards of computer monitors. They would look perfect, they weren't bulged, they didn't smell, they were not leaking electrolyte. You would test them on your cap meter. At that time, I had the Chung instrument meter in my Fluke 12. They'd measure perfect. They're 1 microfarad, they're right on the money. And yet, until I got my Bob Parker ESR meter, that showed me that their equivalent series resistance, which should have been less than 1 ohm, was over 100 ohms, I never realized those caps were the problem. So if ESR is 1/10 of an ohm out of range, it doesn't matter very much. But if it's way out of range, that's your problem. So yeah, high ESR, change the cap. Now, I've had people comment, oh, that cap, that was, ESR was 1 ohm over. It doesn't matter. 1 ohm over is not going to matter. But 100 ohms over, 50 ohms over, yes, it's going to matter. Now, the next thing, shorted cap. I don't see that too often. Other people seem to run into shorted caps all the time. You can test that with a multimeter. Obviously, you have to replace a shorted cap. And then we're back to where this episode started. Number 6, is capacitance within plus or minus 20%? Well, if it's much out of 20%, then I start scratching my head and saying, gee, maybe I should change this. But I've also taken apart and worked on the power supplies of LED televisions and LCD televisions, mostly LCD TVs. And you might find a 1,000 microfarad cap, and that cap is reading 650 microfarads, and the TV's running. And you say, how could this possibly be? And you replace it, and the TV still has the same symptoms that you're chasing. So that 650 microfarad cap that should have been 1,000 microfarad, that was not causing the problem. And then we talked about this earlier. When you put your meter on the cap, number 7, is capacitance stable or is it running? Is it going up, going down? If it doesn't, it should stabilize right away. If it's all over the place, you can set your meter on min-max and you see it drop and then come back. Yeah, replace that cap. Now here's another tip. I don't really want to argue with anybody. My point is not to argue. It's just to share experience. If you find it valuable, great. It's free. It's wonderful. If you don't find it valuable, it's fine. But here's a good tip. When a cap starts to go bad, often the device will begin to run hot. And you'll see a brown mark, sometimes a charred mark on the printed circuit board. So the area where that cap is going to change color. The board will change color. And if you look carefully, you'll see that the PCB is a lot darker. Again, in some places, it almost looks like burnt toast. Well, obviously, there's something wrong with those caps. And when you pull the caps in that area, you'll often find, who knows how many of these 7 things. You'll find that capacitance is running, it's lower than 20% of its like 80% value or 70% value. You'll find ESR could be way too high. Could be any of these things. So if you see evidence of a burned PCB where the cap is, probably should enter that here. Number 8. Is PCB burned underneath it? Yes. That's good reason to suspect and change those capacitors. So that's my experience. I hope it helps someone. I'm really not here to argue. If you think all of these things are okay, perfectly fine with me. Doesn't bother me whatsoever. I have nothing to sell. But if you're new to electronic repair, then you might find these things very useful. So I hope this helps someone. Thanks for watching.